So today is just the last technical lecture. Okay? Hopefully, I just gonna sketch what remains about MacFlow to you. Okay? And so next class Thursday, I'm just gonna tell you what is beyond this class. I actually didn't really finish the whole plan of what I want to teach, and I just gonna tell you what is interesting. And also on Friday, maybe you can just prepare anything. It's gonna you can just chill and do nothing too. But if you have any question, I'm happy to answer. About the area, about adjacent area, connections, doing research in general, anything. Okay, so now about the work. So for the scribe, it really is just I need to just put the deadline because I need to submit the grade. That's all. So so please submit your scribe before December 18. This is likely the hard deadline. If you submit later, and I need to submit the grade before that, it just can be. I cannot just grade that. Okay. But if you submit it and before, and I have time to look through it, then that's good.
We still need to talk to you before we.
Maybe once you're done, send an email, let me know, and then I gonna go through it. And if I actually have some question, maybe I will just send email to you. That we might need to talk and change something. Okay. Now I will after this week I will start to travel already to India and then to Australia and then to Thailand, many places. But we will need to so there's gonna be an exam, hopefully, just to kind of I don't hope to test you really. It's just hope to help you understand things, right? So the date is gonna be around this date, 4 days here. So I will give you the slot, put it on the same place, and you can book it before. Now the time is going to be more than last time. It's going to be actually 40 minutes. Okay. Why is that? And also it's going to be much more helpful, just like our last exam, right? When you can draw something on the board. So if you can have some gadget that you can draw, that would be really helpful. If you cannot, maybe just let me know so that I have some way to can think of the way what can we do. But do all of you have at least some way to write when we meet online, at least in this room? Do you?
I think OneNote should be okay, right?
OneNote is good. Yeah. Right. Just some gadget that you can draw. Yeah. Okay. Good. Yeah, Zoom has this whiteboard on their own too, and you can use that too. It's worse than OneNote, but. Okay, so what's we gonna do in this 40 minutes? Well, 15 minutes is just for exam, similar to last time. The content, I will not ask anything before midterm, just because we don't have much time. I'm just gonna ask something after the midterm. Okay. So what do I mean? So let's be clear. Okay. Okay. So basically, starting from this thing. Okay. Starting from dynamic shortest path and push the label and so on. Okay. And example of questions is kind of something like this. So the main thing that we have learned is like approximate 1 plus epsilon approximate max flow in underrated graph using multiplicative weight updates. And the big one that we have spent many lectures to learn is this one, exact max flow in directed graph in n squared time. Okay. So I want to ask you something like, what are the key algorithmic components, how they combine together, something like that, right? Like you need to be able to identify what's like for undirected max flow. Like we start with 3 flow specifier, how they combine with weight updates. Okay? What's the intuition on expander? Like the intuition there is quite clear. Okay? So something like that. Here I'm gonna go through this actually today, like a lot of how everything fit together today. Okay? Also, push reliable, right? We use push reliable to approximate expansion, whether it's like at least phi or at most phi log n, phi log square, something like that. It's like how push reliable and cut matching game combine together to approximate expansion. Okay? And also expanded decomposition. Okay? So something like that. So that's the kind of topics that I expect you to have some intuitive understanding. Okay. I might have I might ask some 2 more simple questions about push level. I will announce this, put this specific question as some question optional homework. You don't need, please don't submit it. I will not grade it actually. Yeah. But I might ask this question in the exam. Okay. There's gonna be like a two more application of push level. Yeah. Small one. Yeah. So that's basically, this thing is basically kind of already what we have learned actually. It's just I want to put it there so that you know that you put it there explicitly that you know that how to apply what you have learned to this question. Okay, so that's the thing about exam question, about the content. Okay. Then another 10 minutes or so, I'm just gonna basically ask you whether you understand your own project. So you just basically say what is in the project. Walk me through your report quickly, 3 minutes, 5 minutes or something, just to see how everything is organized. I might ask you something, what's the point here in your report here, something like that. And you can tell me if it's like a group project, you can tell me your contribution. If it's a group project, this is the contribution can be the same too. Yeah, you just work together. That's fine. It's totally normal. Okay? Just let me know how just so that if you don't understand some part, now I understand that you didn't contribute there, and I can just ask you some part that you put your work there, something like that. Okay. Good. And then if you have some time, you can walk me through your scribe note if you have time. But if not, then the scribe thing is we're just gonna email. So that's online meeting. Last thing in this course. Okay. Questions? Yeah.
Do we have the report in by that date, or is there?
Yeah. Please submit the report before we meet.
Okay, cool.
Yeah. Okay.
Is there going to be just a thing on Gradescope for the report, or should we email it to you?
Oh, I'll put it on. Actually, there are just 6. I put it on Gradescope. Yeah. Right. Okay. More question about logistics. All right.
The scribe note, if you've already like met you and explained it like before, do we again need to go through it again?
Say again.
No, explain the scribe notes part. If I've already spoken to you.
Oh, if all of your scribe you have talked to me, then we will not do this.
Oh.
Yeah. Right. Okay. Okay. Now MacFlow. Okay. Let's finish it up today. So what we're gonna do today is that actually, like, I will kind of tell you how everything fit together, but that's gonna be one part that we will actually not talk in details about. I'm just gonna point you out where you can read if you want to learn, okay. Which is about directed expanded decomposition, the algorithm that we have learned in undirected graph. It can be extended to directed graph, but we don't have time to go over everything, why, how to extend that. Okay, so let's recap. Okay, MacFlow. Okay. So, like, let's recall directed expander paradigm. I mentioned this at some point in class. So the paradigm is that whatever graph problem you look at, just try to solve that problem on expanders, try to solve that problem on DAGs. If you can, then there is a good chance that you can just make it work on any graph. If it's just expander paradigm in undirected graph, there's no second part. Just try your problem on expander, and if it works, it should generalize. Okay. But here there are 2 things. Okay, and now we learned before that we can solve approximate MacFlow on DAGs using weighted push level. I hope you remember, like, if you have tau as like topological order, then like you can put the weight of edges, right, to be something like tau, like the difference in tau of the endpoint, and then you can solve approx MacFlow on DAGs in this time. Yeah. That's some lectures ago. Yeah. Also, approx MacFlow on expander. If it's like a phi expander, and you want 1 plus epsilon, you can actually solve it in this time. Okay. This is to use some push level, like you don't need the weighted version of push level, you just use normal push level here. And like, this is the thing that I said that actually you know how to solve it already using the thing in class. So this is gonna be like in this optional homework for that I may ask you in exam. Okay. But the point is, push level, weighted version or not, like there is a way to just use it to solve DAGs and to solve expander. And once we have this, now basically like the tools in this class, expanded decomposition or hierarchy, once you see these 2 things, you expect that you can solve it on general graphs. Okay. So and this is exactly what we did. Okay. So we have these 2 things, and now we try to make it work on general graphs. Okay. And what did we do? So we learned about directed version of expanded decomposition and SE hierarchy, right? we learned about this definition in lecture 27. And then, okay. And then, actually, okay. Anyone recall the definition of this? What's this thing? What's SE hierarchy?
Indirected or undirected?
Directed.
It's kind of just, it's similar, it's just that our notion of expansion is allowing, is working only in strongly connected components. So it's just like the separator is we're only removing like one direction to turn everything into a DAG. And then other than that, we can still do the same recursion.
Good.
But it makes more sense to just think of it in terms of partitions as opposed to the hierarchical view.
Yeah. Like the definition of directed version is actually just the same as the undirected version. So phi SE hierarchy H of a graph is like a partition up to EL of E such that what?
I mean, they need to be partitions, and then EI is expanding in E or G minus E greater than I.
Good. EI is phi expanding in G minus this thing. Yeah. Is the partition, yeah, is partition of E, right? So, yeah. Okay, so think like you might have some graph such that this is like this is strongly connected because there are some edge here. And now like when you have EL, when you delete EL is expanding in this whole graph. And when you delete it, now you get like this strong component, right? And now like similarly, like you may like there's on each of these strong component, there are like a lot of edges, a lot of DAG edges here. Maybe it looks like this. But now EL minus 1 maybe look like this. Right. Okay. Once you remove EL minus 1, it breaks this strong component into 3 subcomponents and so on. But EL here need to be expanding in this component. This EL minus 1 is expanding in this component. So so that's the directed SE hierarchy. Okay. Like if it's undirected graph, it's just that you don't have this DAG edges. That's all. Okay. And Okay. Do you recall how we construct? So we have this directed SE hierarchy. How do we construct the shortcut graph? Anyone recall this? What does it look like? Okay.
We kind of put a star at each cluster with capacity like epsilon on each edge.
Okay. We put a star on each cluster. Like for each cluster, we put a star. Where are the leaves of the star?
The cut edges in the partition.
Yeah, the cut edge. Yeah. Like we just gonna put a star on like the end point of this cut edge. Like this. Right. You see this? Maybe I should put it up. And here like there is a star. A star. You can put it on one endpoint or two. It doesn't really matter. Yeah. And we put like a capacity of something like epsilon phi times like the capacity of the edge incident to it. Right. What's the intuition about this adding star? Like, does it change the graph significantly in any sense?
Not too much, just because we're scaling the capacity down by epsilon phi. So
Yeah, it will not change like the cut. Like, it will not increase the flow on anything that much, because you see, we add a star between, like, on top of expanding set. The expanding set is already well connected, right? If you find a cut between any expanding set, there is a lot of edges crossing it already. Here we're just gonna add some star edges that cross this. But these star edges will has small capacity. So yeah, like what I mean is like if this is some component, if this is expanding set, yeah, let's say this is expanding set A. And now look at any cut. Look at any cut here. The cut here is kind of bigger than phi times, maybe this is S times AS already. But the star that we add, how much does it contribute? It might contribute to like the cut here is like contributed to like this thing contribution is like epsilon A. So this is like a kind of epsilon fraction of the cut. So this doesn't really change the cut size or the flow size. Yeah. Okay. Right. Okay. So that's the shortcut graph. How do we define the weight of the shortcut graph? The edge weight of the shortcut graph. Like there are two types of edges: the original edge and the star edge. Yeah, Michael.
Star edge is the size of the cluster.
Yeah, for star edge. Here, if this is like call it h, the weight here is like just the size of the cluster. Okay. What about the original edge? Yeah. Like from here, we need to like the original edge, if you remember, defined by tau, by some ordering. How do we define ordering from here?
SC hierarchy, like the base partition should give us like a DAG.
Mm-hmm.
So we can just use that topological order, I think.
So let's see. Yes. Let's see. That's the idea, but I don't know if it's the like once you have a DAG, there are so many topological order that works. I'm not sure if it's gonna. Let me describe, and then we see. Like when you look at EL, once you remove EL, it gives you these three components, right? This three component has ordering, some topological ordering of the three components. Like H1, H2, H3, right? So what you're gonna do is like to put H1 to be before H2, before H3. That's the ordering, tau. And then like once you remove EL minus 1, it breaks things. Like it kind of define the ordering of components inside this component again. Right? Like maybe this is H prime, H2 prime, H3 prime. So now it's a kind of, you can put ordering of this guy. H1 prime, H2 prime, H3 prime. If you recurse until the end, now it's really, this is a kind of coarse grain ordering, and you can make it more and more fine grain just by going top down. That's the, and then that gives you the ordering of the whole set of vertices, right? Now, if I just say I look at the DAG edges at the end, I'm not super sure. Does it give the ordering that is consistent with this thing? I think it should. It should. Like
Consistent, right?
yeah, it should be consistent. Like you cannot hope that there is some guy here that appears before some guy here. I think, is it? I am not sure. I'm not sure. I'm not sure. Okay. Okay. Anyway, like so now given this tau, what's the weight of original edge? It's just the same thing, right? For any edge or original edge, you just put this. That's the weight. Okay. So that's how you define shortcut graph. And then we learned that, okay, if we run weighted push level on the shortcut graph, then we basically get approximate n squared time Maxflow algorithm. But if you have approximate Maxflow algorithm on any graph, on any directed graph, now you can make it exact. Right? Just by solve approximate algorithm, get an approximate solution. Now repeat in residual graph. So, okay. So that's how we try to generalize the DAG algorithm and expander algorithm using SE hierarchy. Okay. So it kind of works. It works. But we did assume two things, right? We assume that, okay, first, you can construct this SE hierarchy fast. And also, when we try to solve weighted push level on shortcut graph, we kind of get the flow on the graph with star. We need to, but what we want at the end is just to get the flow on the original graph without star. So we need to be able to kind of project the flow on shortcut graph down, like to original graph, removing star, okay, without causing so much congestion. So this one is important. This second one is kind of, the second one is a smaller concern actually, but I tell you how to address it. Okay. But the first one here, we basically address it using the thing from last class, the leaky version of S hierarchy. Okay, so let's look at the first assumption. How do we build this thing fast? Okay. So last lecture 30, okay, we introduced this leaky SE hierarchy. Anyone recall what's the definition? What's the, or at least intuition of what it is?
Like the
Sam?
flow is allowed to leak outside of the cluster, basically. Like you can go out and then come back in. Yeah.
Good. Yeah. The flow can go out of components. That's basically the correct intuition. Meaning that when you have this set, the green set here that is expanding, is supposed to be like from this definition, this green set is supposed to be expanding inside this component. This thing is expanding the green thing. Just look at the green thing. Each of the green thing is expanding inside its own component. But now the leaky version is just to say that, okay, they are still simultaneously expanding, but the flow that certify its expansion can go out of the component. Okay. So what we formalize this by saying that the leaky version is that now EI is phi expanding in G, not in the component, but the how it's expanding is just this constraint. Okay. It just needs to be certified expansion of only EI in this component. Okay. So like only demand between the component inside here need to be expanding, need to be routable with low congestion, but you route it in G. Okay. So this is like a kind of relaxation. It relaxes from here to here. Okay. Right. And now what's the nice thing about leaky version of SE hierarchy is that now we have a bottom-up algorithm instead of top-down algorithm. The top-down, so we can use expanded decomposition bottom-up instead of using expanding balance separator. Okay. like the non-leaky version, we can build it, if you remember, top down using expanding balance separator. But here the leaky version admit top bottom up. Okay. So let's recall the algorithm. The algorithm is really simple, right? Like you kind of start with put all edges at level 0. Think of Ci as like edges at level I. Start every edge at level 0, and then you kind of keep promoting edges. So what do? We just say that, compute leaky expanded decomposition with respect to Ci. Any edges that you need to cut, you promote it to level I plus 1. And repeat. Look at the next level. Now compute leaky expanded decomposition with respect to the next level and promote it to another level. So like when we choose phi to be small enough so that the number of edges that is promoted to next level is just getting smaller and smaller by half. So there's going to be log n levels. And EI is just set of edges that has been promoted to level I, but not above, not going further. So, so that's the algorithm. Now what's the advantage, right? The intuition is this. The advantage of bottom-up approach is that, let's think in unrelated, even in this advantage is even there in unrelated graph. So the point is that constructing the bottommost level is just easier than the topmost level. How? Because if I want to construct the topmost level of SE hierarchy, the way that we learn, and the only way I know actually, is to use first just compute expanding balance separator. Now that algorithm requires black box max flow. I don't know how else to not use it, or like some approximate max flow. But now, in contrast, if you look at the bottommost level of this, what do we need to do here in the bottommost level? We just look at like when I is 0. We just basically compute phi ed of degree E, which is just degree of the graph. Okay. So when we compute some expanded decomposition of the degree node weighting of the whole graph, usually it becomes simpler. And we see how to do it already actually. We saw that on unrelated graph, we know actually how to solve this thing, how to solve expanded decomposition with respect to node weighting, with respect to degree node weighting in this time, nonlinear time, just by using standard push label, right? So there are ways to just from here you see that there are ways to bypass black box max flow. Okay. So the point is, bottom up, at least the first level from the bottom is easier than the first level from the top. So this is a kind of, at least our intuition when we develop this algorithm. Okay. So this looks easier, and we know how to build the first level already. The first bottommost level we know how to bypass black box max flow. Now, once you see this, like now the question is like, okay, the bottommost level you can do, but why can we hope to keep building the next level again and again? Because this is not clear anymore, right? Because once you go beyond the bottommost level, now you need to compute expanded decomposition with respect to degree of CI. It's not degree of G anymore. Now it looks harder. So, okay, how do we deal with this, right? Okay. But the thing is that it's still, okay, how can we hope to construct the next level of SE hierarchy? Okay. This is where we use the crucial property of bottom-up construction. Like bottom-up construction has one crucial property that when you try to build the next level, when you try to compute the expanded decomposition of ECI, if you look at all edges of level below, that form a hierarchy of the graph below already. Just more precisely, like if you the sentence that I kind of remember intuitively is just when we try to build a level I hierarchy, the level I of the hierarchy, we have the hierarchy up to level I minus 1 already. Okay. So more precisely, when we try to compute leaky expanded decomposition with respect to degree of CI, we already have SE hierarchy of this graph, G minus CI. This is so important. Okay? That this is the thing that we proved from last class, and it's really just crucial. Okay? So you see, like when we try to compute this thing, if you look at, you can just look at the edge of level E0 up to of level 0 up to I minus 1 at that time. This edge set is the SE hierarchy of this graph. So that's kind of basically, like we know before that given the hierarchy, if we get a whole hierarchy of a graph, it helps you. It helps you like computing max flow and so on. Now, this thing just said that, okay, it kind of, in the process of trying to build this, to build the next level, you kind of have a partial hierarchy of the graph that you want to work with. We want to we want to compute the SE hierarchy of if we have the full SE hierarchy, we even have like a max flow algorithm, right? Because we know how to get max flow algorithm given the hierarchy. But here it's like you get hierarchy of almost everything except CI. And now you want to get expanded decomposition with respect to CI. So it looks helpful, yeah.
The SE hierarchy there, it's a leaky one.
It's a leaky one, yes. This is leaky. Yeah. Okay. So I need you to understand this intuition, how bottom-up approach is more it's kind of more convenient for you. Questions about this? Make sense at all? Question? Okay, too quiet. Yeah, ask something like okay, where did I lost you or anything? Yeah. Okay.
Yeah, what I remember is like we can build this without the like bottom layers. What's the intuition here?
How to build this? How to build this thing
Yeah.
on the?
You want to be that we can build this like only with any of the basic CI. But yeah, why do we still need the bottom up layers?
Right. If we have black box MaxFlow, we can just compute expanded decomposition for any node weighting. That's okay. Right. Now we don't have that. We don't have black box MaxFlow, but we still kind of want to compute expanded decomposition with respect to this node weighting, which is not the whole graph. How can we do that? On one hand, we know if we have black box MaxFlow, we are done. On the other hand, if we have the hierarchy of the whole graph, if we have hierarchy of the whole graph, of the whole graph, we can build a shortcut graph and we get another black box MaxFlow. Okay, we get this thing, which is like some n square black box MaxFlow. So if we have the black box MaxFlow, that's good. If we have the whole hierarchy of the whole graph, we're good too because we get a black box MaxFlow. Now, the thing is that here we need to we want to compute expanded hierarchy of some node weighting, which is not everything, not the whole graph, not degree of G. But what we have, we don't have quite a full hierarchy, but we do have a hierarchy of this graph. I didn't tell you how do we exploit it yet, right? But it is something that basically is almost what you want. Yeah. Okay, more question?
Yeah, I guess I just don't understand the intuition on like it looks pretty close, but it's like we still like are we going to be like doing some sort of like
We're gonna just use like this gives you some hierarchy of not the whole graph. You can just define shortcut graph based on that too. Like
that's like good enough for the next level.
and that's like and just run weighted push level on that, and it just basically good enough. I didn't explain why, but like it's just that if you have a full hierarchy, add a star on every expanding set, you can get MaxFlow, approximate MaxFlow. That's okay. Now you don't have hierarchy of the whole graph. Still just can put a star on every expanding set, and then run weighted push level. Turns out that it's just good enough to build this thing. Okay. Right. More question? Okay. Right. So that's the point. When we try to compute leaky ED with respect to CI, we already have a hierarchy, like a partial hierarchy HI of G minus CI. Let me call this partial hierarchy. Right? We need to exploit that somehow. Okay. But the point now is that everything now reduced to computing leaky expanded decomposition given this partial SE hierarchy. Okay. So now this is the problem that we need to do. Like this problem, SE hierarchy construction reduced to construct leaky as ED with respect to CI, but you get a hierarchy of G minus CI. Now, last class too, we learned how to compute leaky expanded decomposition. Okay. Anyone recall the definition of leaky ED?
I mean, it's kind of it's expander decomposition, except we only require the constrained expanding. And
Yeah. So, yeah. Tell me. So, leaky ED is like if your input is a graph and phi and A, then what it output is the cut of edges of the graph, right? Such that the size maybe is like something, maybe kappa, a slack here, times A. That's one. And we used to have that C, A is phi expanding in G minus C. That's not leaky version. What's the leaky version?
we just require it to be G minus C constrained phi expanding
Yeah,
in G.
right. Now it just need to be this constraint phi expanding in G, just in G. Okay. Yeah, it's a weaker version. Okay. And the key point of leaky expanded decomposition is that you don't need expanded trimming. Okay. We kind of the point of expanded trimming is so that the expansion is kind of within the component. Now we don't want that. We don't require that, so we don't use expanded trimming. And this is quite crucial because in the related graph, we actually don't know. We don't know how to do it. I think it's a good open problem. Yeah. How to get expanded trimming for any node weighting. If I like assume black box max flow, I allow you to do that. How to do it? I don't know. In undirected graph, we know. Just call one max flow call from the battery, right? If you remember, and that just you're done in one max flow. Question?
Never mind.
Okay. Good. Yeah. So we don't know. When the node weighting is degree, there are some algorithm, but for general one, I don't know.
Wait, sorry, is it like an existence question, like whether or not you can?
Even existent question.
Oh, okay.
So yeah. One second. If it's existential question, maybe there is some way to do it by, let's say, you just say you just keep cutting. If there is a sparse, let's say like you start with like a node weighting that is expanding in G, and now you want to be expanding in one component, you just check if it's not expanding inside the component, there must be a sparse cut. So keep cutting, just be greedy in that way. That might work, yeah. But I don't know, like you can check this, yeah. That should work, like it give you something. But this version will be exponential time.
Right.
Yeah. So how to get something similar even in polynomial time, let's say. It's exponential time because just checking for sparse cut exactly, that's NP hard. Okay. But anyway, like we now just want leaky ED. We want leaky ED with respect to CI given the partial hierarchy. If you want, like, so since we don't need explicit trimming, the whole thing basically just reduced to balanced sparse cut or giant expanding set with respect to CI, right? Like that's the whole algorithm of expanded decomposition, if you remember. Just either find balance cut or it's not balanced and you're kind of done on one side. Okay. So that's now reduce the problem to this. Balanced sparse cut or giant expanding set given partial SC hierarchy. Okay. So that's our problem now. Either find balanced sparse cut or giant expanding set with respect to CI given the partial hierarchy of G minus CI. Okay. This is the part that I will just hand wave a bit. Okay. I will need to hand wave a bit because we don't have time. But let's see what did we do. Okay. So in undirected graph, okay, we learn how to get balanced sparse cut or giant expanding set several times. Okay. For any node weighting, we learn how to just basically kind of combine. This is your homework. This is in your homework, like in some 2.2 or something, where you use cut matching game with deletion together with black box max flow. If you remember, like you kind of apply cut matching game, you have A and B, and if you send out the flow, that's good, you're done. If you don't send out the flow, there's some cut, with some cut S. Basically, you kind of deactivate all guys here to delete all this guy, and then match the rest. The max flow will match the rest. Okay. When the node weighting is degree, okay, we don't need black box max flow. We just use cut matching game with deletion, but then we use dynamic push level. Okay. Like if you just use push level, it's kind of already good. It can define you a sparse cut with respect to degree, and also kind of send out the flow. Except that without dynamic version, there is something not good enough. Do you remember what is that?
Is it that you just don't know how to handle the deletions? Like that you can cut them
Yeah. But there is something more specific about like how you mesh this. Like the flow from A that is not cut might actually mesh to something somewhere bad. Where is that? So yeah, the flow might actually go to mesh this thing. Like the flow might go to mesh the thing that you delete and that you don't like. Yeah. This is the kind of question that I might ask. Like this high level understanding. So, but with dynamic version, we can prevent this from happening. A reason is that like we basically make sure that in the dynamic version, every edge crossing the cut have flow in the correct direction. There is every edge, every cut edge is saturated by a flow in the correct direction. So you cannot actually send flow crossing the cut. Okay. So this flow will basically need to mesh to somewhere where you don't delete. Okay. Anyway, we learned this thing. We learned how to get balanced sparse cut or giant expanding set on the reduced graph. Now, in the reduced graph, both of these cases is actually both of the case is shown in this paper by alumni actually, Henry Fleischman and Jason Lee, my colleague that we work on many papers together, and Josh Lee, just this year. So one can show both of this in unrelated graph. Like if you want to get the expanded decomposition for any node weighting, you can use black box max flow. If you do it for degree, you can use some version of push level. They need push pull, like dynamic push pull level. They need that, but yeah. But it's an extension and requires some new nice idea. And I will not have time to go over this paper. Okay, so that's kind of what's known. Yeah. Now, the algorithm here will use cut meshing game too. The one in the related graph here. So it kind of just suffice to ask, what do we need to solve per round of a cut meshing game? That's what we need to solve. So what we need to solve in each round of a cut meshing game will look like this. Recall that this is a problem. Yeah, right. We want to solve this thing with respect to CI when you get SE hierarchy of G and CI. So the thing that we need to solve is like, imagine that you have a graph and then the node weighting is like CI. The node weighting A is like CI, degree of CI. So think of this as like maybe endpoint of CI. Is like a CI, right? And then what will happen in cut meshing game is like you're gonna get like the set A and B, and you need to route between A and B. You want to route between CI. and just see if you can get sparse cut or not. If you can route, then that's good. You've completed the route of cut matching game. But also, what you have is that you have a hierarchy of G minus Ci. Okay. Just note again that if Ci is everything, then this is it just means that you don't have a hierarchy. And you just want to find sparse cut. Like you either find sparse cut with respect to Ci or send flow from AI to BI. Let's call this AI, BI. And maybe I delete this A. Right? This is kind of what we want to do in cut matching game. Right? Send flow or find sparse cut. Actually, it's kind of more than that. We want to do like AND version, where like you either find cut and match the rest. Right? Okay. Just note that if Ci is everything, if Ci is all edges, then you don't have a hierarchy. And this is just with respect to node degree node weighting. And we know how to solve this. We learn we learn how to solve this just by using push level. Okay. But now we just want to do it for some set Ci, and you get the hierarchy of everything else. That's the question. Is it clear? That's the thing we want to do. Okay. Now here's a claim. You can define call this thing Hi. Okay. Now what you need to do is just define a shortcut graph with respect to Hi. Yeah. Shortcut graph. And then run weighted push label on it, on this thing. And it will basically give you the flow, right? Okay, the claim is that this thing, you can use it to solve this one in n squared time. This is precisely where I kind of exploit the hierarchy, the partial hierarchy. Okay. This is where I exploit the partial hierarchy. If I get the hierarchy of the whole thing, of the whole graph, it will either give me approximate max flow or approximate min cut. But here I don't have quite that. I have a partial hierarchy, so it will not give you approximate max flow and min cut. It will just give me sparse cut, which might not be approximate min cut. It will just still be sparse cut with respect to Ci or send flow. Now, this is the thing that I hope to teach, but we don't have time. But now it's not too long actually. It will fit in one lecture, but we just don't have time. So let's see. Yeah, this is just what I said. Okay. But if we can solve this, thing, then we're done, right? We basically solve balanced sparse cut or giant component or getting giant expanding set with respect to this thing. And given this balanced sparse cut subroutine, you get expanded decomposition. Getting expanded decomposition, you get the hierarchy. So that's how you resolve the whole thing. Like you get the whole hierarchy fast. That's the okay. Just to summarize, you reduce leaky ED. Actually, leaky SE hierarchy is reduced to leaky ED, and leaky ED is reduced to balanced sparse cut or giant expanding set, and this thing is reduced further to cut mesh, the thing that we just said, either find sparse cut or mesh a lot of things. Okay, so it's just a sequence of reduction, and we saw this reduction, like this one we saw it completely. This one and this, like this 0 one, we saw it completely. The first and the second one here, we saw it in unrelated graph, and it just extend to the related graph. How exactly? Read the FL paper. It's still not quite simple actually. The paper is still quite long, 50 pages still. But how to solve cut mesh? Using partial hierarchy, this thing here, this picture here. Why this thing works? Like the algorithm really is just this. Okay, just build this shortcut graph and run weighted push level. And why it works? That's quite simple. Can be taught in one class, but we don't have time. But if you want to learn, just look at my paper here with Aaron, Jason, Joachim, and Tawei. It has 7 pages, not too simple, but kind of quite readable actually, quite simple actually. Okay, so that's how you can get the hierarchy without black box. Okay. That's basically how we address the first assumption. For the second assumption, let me tell you quickly how to project the flow on the shortcut graph, the flow on this graph with all the star, and remove all the star and get the flow on original graph. Okay. This is a question of how to remove stars, really, right? So let's simplify ourselves and like look at the warm-up case where we have only 1 star, and let me tell you how do we remove 1 star. Removing any other star is just the same. Okay. So to be kind of super concrete, what I want to say is this. Let's say that you have a graph, and let's say that you have a set A that is expanding. And now let's say that we have a star here, right? This is a graph GA after adding a star. And I would say that I can preprocess the graph a bit, so that now given any flow in the graph, in the shortcut graph, I can get the flow in original graph with that router send demand, with basically not too much congestion. Just how to remove 1 star. Okay. How do we do this? Well, the way to preprocess is this. If A is expanding, what we're gonna do is we're gonna just kind of route. There's gonna be like another graph X such that kind of this graph, I can embed or route this expander X. This is expander. Okay. With congestion like log n or log square. Yeah. We can embed this expander into G, sorry. In G. Yeah. With congestion log square over phi. If A is phi expanding, we can route an expander such that the node weighting of expander is just A. Degree of X is A. And the congestion is something like 1 over phi. How do we do this? Like this thing is just like a certificate, right? For expansion of A. How do we do this? If there is some expanding set, how do we embed expander into that set? Do you know what I mean by embed? I just mean like we route this demand. We route X. Yeah.
So is this what cut matching game is doing with the max flow calls?
Exactly. This is just what is cut matching game is doing, right? When you run cut matching game on top of A, on top of the node weighting, you just kind of on one route you route like some matching between A. Like after log square round, you really just embed this expander X into G, where the node weighting is basically A. Okay? So you can certify the expansion by embedding expander. That's what is cut matching game is for. Okay. Just use cut matching game. But now the point is now that if X is some cut expander, like think of xi here as constant. Yeah. Given any demand on X, if this is X, give a demand on X plus 1, plus 2, minus 3, plus 1, and minus 1 here. You can route on this expander using just push label. You can route this. And how? Yeah, this is basically the second problem in homework 4. Okay. Really just kind of use push label with large enough height. You're gonna route most of the flow and then try to route it. Okay. I kind of guide you in this thing, and you should solve this. Okay. So the point is, given an expander and demand, you can route any demand fast with some congestion. So expander is just easy to route. That's basically kind of what you remember. You can route if the whole graph is expander, you can route it fast. Okay. So now with these two ingredients, what do? Suppose that you have a flow, and some of the flow path go through a star, and what you want to remove star. What you need to do is just, instead of going through star, you look like, maybe look at this A, B, C, D. There's going to be A, B, C, D in X, right? Now you can route on X maybe you route on X like this. Maybe this is another one flow and another flow. Maybe this is like yeah, X and Y. This flow, this path will kind of correspond to some path here and another path here. Because every edge in X is embedded, is routed in G. Right? So look at this demand. To remove the star, it induces the demand on X. You route on X exactly, you route that demand exactly. Look at the flow here, embed it back. This is the flow that you route on X can be embedded into G. Now you completely remove the star. Make sense? Yeah.
Wait, how do you embed the flow back to G? Because the flow is in X. Right?
No, like this is the flow in X, but the whole graph X, every edge in X, you can embed it into G using cut matching game.
Oh.
Wait, maybe I'm just a little confused here. So doesn't like embedding the expander via the cut matching game require making calls to max flow? Or okay.
Oh, you mean like how to this? It seems like I'm calling max flow here.
Yeah.
Yeah. So good. So right now, let's say that we use X. I'm gonna address that now.
Okay.
But the point is, if you have this X that is embedded into G somehow, you can just route on X and then embed it into G.